In this lesson, we'll be talking about contrapositive proofs. Recall that a statement, P implies Q, and its contrapositive, negation of Q implies negation of P, are logically equivalent, simply meaning that if one is true, the other is true. If one is false, the other is false. With that said, if we prove the contrapositive of a statement is true, then we have proven the original statement is true. Here's some good times to use the contrapositive. If your assumption, P, is hard to use, but the conclusion, and especially the negation of the conclusion, is easier to use, you might want to do the contrapositive instead. Also, if you're working with an assumption about some set being infinite, this is really hard to get your hands on, so it helps to be working with something finite. Here's our first example. Let A be a set. If A squared is infinite, then A is infinite. Now if I were to try to tackle this directly, I would have that A squared was infinite, and somehow from that I would have to prove that A is infinite. That's kind of difficult. It's hard to even say let A squared be infinite and then use the word then. Then what? However, contrapositive will help nicely here. We're going to use proof by contrapositive. And when you write a proof by contrapositive, it's nice to put a little bracket in and write down the contrapositive specifically. It doesn't really add to the proof to include this, but it does help you as the writer in order to be able to follow your steps. Here's the statement of the contrapositive. Remember, we switch the two, P and Q, and we negate both of them. So we have if A is finite, then A squared is finite. Now let's prove it. Let A be a set, just to pick it arbitrarily, and assume that A is finite. So we've picked up our assumption that A is finite. Well, what does that mean for A to be finite? Then the cardinality of A is equal to n for some n in the natural numbers. Now we need to somehow work with A squared is finite. Well, what is A squared? A squared is the set of all ordered pairs of elements, with both elements coming from the set A. Thus, the cardinality of A squared is equal to. Well, let's think about that. Remember, A squared simply means A cross A. It's the Cartesian product of A with itself. And also, the cardinality of the Cartesian product was the same thing as taking the cardinality of the first set times the cardinality of the second set. We've basically got it at this point. The cardinality of A was n, and then the cardinality of A again is n, so we get n squared. We have that the cardinality of A squared is equal to n squared. That makes it finite. Therefore, A squared is finite. And this finishes the proof. Now, one thing about the proof by contrapositive is, again, your reader knows that if you prove the contrapositive, then you've proven the original statement. So we don't need to make any sort of summary statement saying, thus the original statement is true by contrapositive. We don't need anything like that. We'll just prove the contrapositive and let our educated proofreader know that we proved the original statement at the same time. Here's the next example. For all x in the reals, if x cubed is greater than or equal to 0, then x is greater than or equal to 0. If you think about cube roots, this is kind of obvious. However, cube roots are not something that I'm necessarily allowed to do. If I were to take a cube root, well, what is a cube root? What does it mean for a cube root? Do we have any rules about cube roots? Unfortunately, no, we don't. What we do have, though, is we have the rule that any real number squared is greater than or equal to 0, and we know that if we multiply both sides of an inequality by a value, it will stay the same if the value is positive, or it will flip the inequality if the value was negative. With that said, it would be much easier if my assumption came from right here, and I was just looking at x instead of at x cubed. Let's use contrapositive. Here's the statement of the contrapositive. If x is less than 0, then x cubed is less than 0. Remember that when you negate the concept of greater than or equal to, it becomes strictly less than. Now let's do the proof. Let x be an element of the reals and assume x is less than 0. Now remember, we want to show that x cubed is less than 0. What we could do is multiply both sides by x squared to get to x cubed, but we don't know for sure that x squared is greater than 0. We know because x is a real number that x squared is greater than or equal to 0, but we need to make first a claim that x squared is greater than 0 so that we can multiply it. Here's how we'll do it. Multiplying both sides by x, we get x squared is greater than 0. Notice that I multiplied by x, which was a negative number, and that's why I flipped my sign. So now that we have that x squared is greater than 0, I can multiply by x squared to get x cubed right here. Then, by multiplying x less than 0 by x squared, we get x cubed is less than 0 as desired. Here's what we did in this lesson. How do you prove a statement P implies Q by contrapositive? What do you think? Prove the contrapositive. Negation of Q implies negation of P. Since this is logically equivalent, you prove the original statement at the same time.